I'm Jon Siegel, and we're at my shop in Wilmette, New Hampshire. And today I'm going to talk about metal turning tools, metal machining tools, and specifically high-speed steel square bits and how to shape them, how to grind them. And then I'm going to demonstrate 3 different machine tools that utilize high-speed steel square bits. So to start with, we're going to look at the stuff on the table here, which are square bits like this. This is the topic for today. And all the different kinds of tool holders that utilize square bits, either on a lathe or a shaper or a planer or a boring bar. And I have examples of all this up here. So I'm going to start with a little bit of history of this. Starting in 1792, when Henry Maudslay invented the screw cutting lathe as we know it. So usually you think of metal turning lathes in the modern sense, or engine lathes as they were called, starting around 1800. So for 100 years, from 1800 until 1900, metal turning tools looked like this. And it's a solid piece of steel, a single piece of steel, and the nose has been created this way by a blacksmith who eventually just put it over the edge of the anvil and hit it like this to bring this up. And then it was heat treated. And then the machinist would simply grind the top of the tool to sharpen it, or maybe the front to some degree. But essentially this was not sustainable because eventually this got lower and lower, and the nose that the blacksmith had created got smaller and smaller. And then you had to take it back to the blacksmith, who would heat it up and bang on it again and bring it around, and this would get shorter and shorter. But it had to go back to a blacksmith to be renewed periodically. So then, 100 years later, starting around 1900, specifically in 1893, exactly 100 years after Henry Maudslay, the Armstrong Company invented this. And so we went from this to this. And this is truly revolutionary because the tool steel is only this. And this is a tough forged piece of steel. But it's not tool steel, cutting steel. This is the only, so you save an awful lot of money because the volume of tool steel that you're using is now only this piece. And right about the same time, high-speed steel was invented. So before there was high-speed steel, there was carbon tool steel, which was great. For 3,000 years, we had carbon tool steel. It was invented in Anatolia, 1000 BC. And that was when they learned how to heat treat steel and manipulate the crystals. Then that was the end of the Bronze Age and the beginning of the Iron Age. So that carbon tool steel was great for thousands of years. High-speed steel was invented around the turn of the century and became popular into the 1920s and 30s. During World War II, it was used universally and completely replaced the old kind of carbon tool steel for machining. So what is high-speed steel? And why is it called high-speed steel? So high-speed steel is essentially just your tool steel with a 1% carbon or 0.8 to 1% carbon, but it's got other additives in it. It's got tungsten and or molybdenum. The first ones were just tungsten, a substantial amount of tungsten. We're talking about 15 to 18% is really a lot. And it was discovered that additive had a huge effect on the tool steel. And in particular, it caused the tool steel to not lose its temper at high temperatures. So the overheating of the tool and causing it to lose the crystal structure or its temper, which had plagued machinists for 100 years, suddenly became a non-issue. Now we had a type of steel that could peel off chips. The chips would come off the lathe red hot. And that didn't bother the tool at all. So, because this was very important in the war, right? Because you had to crank up everything to maximum speed, and speed was so important. And so this type of steel, which is sometimes called self-hardening or air-hardening steel, became known as high-speed steel because it allowed the machinists to run everything at 2 or 3 times the speed that they had been going before. So Armstrong invented these tool holders. Some machinists, back in the day, machinists were suspicious that how could this little screw hold that bit well enough to create a system that was as rigid as this thing that they had been used to.
So that's just one big chunk of carbon steel.
Yes. But, you know, that was more of an imagined problem than a real problem because the screw, generally the diameter of the screw is equal to the width of the bit. It's quite a substantial screw. It has a lot of engagement. The metal that it's screwed into is pretty hard, and the screw itself is hardened. And the strength of these clamping screws is quite substantial. And the problem of the bit wobbling around in the hole is really not a problem, even though in the early days people were suspicious that it would move around and cause problems, or vibration or anything, which it doesn't do. I guess I'd like to show this. All right, so this is a page from Machinery Magazine, August 1909. So if the patent, the Armstrong patent is 1893. Right, so this is about 10 or 15 years after the patent. They're publishing full-page ads in the machinery magazines. So here's a whole set of the one-piece tools. So here we are in 1901, and we're still looking at the old-style tools, but also the new-style tools were also coming along. So look what we have here, okay, also from 1901. We have an illustration of the Armstrong patent. All right, and then here, just on this page here, you have the one-piece tools, and here you have the tool holders. Here's the one-piece tools, and here's a discussion: advantages of tool holders. Right. Well, obviously, the advantage of tool holder is that you're saving so much money on the cost of the tool steel. You're probably familiar with this book because this book has been reprinted, you know, hundreds of times. You know, back when South Bend started, they supplied this book with every lathe that they sold. It's called How to Run a Lathe. And this particular one's from the 40s, but they kept updating them over and over throughout the years.
This particular image is classic. You find it everywhere.
Yeah.
As far as, you know, what the bits should look like.
Collect all these bits. I collected all these bits because I go to tool sales and I buy boxes of junk and I sort through them. And there's always a bunch of these lying in the bottom. Half of them I just throw away because they're too short or they're messed up. But a lot of these had been worked by someone else, and then I either rework them or I cut the ends off or, you know, whatever. So a lot of times I can get what I want by taking something that's close to what I want. And then I can do less grinding, you know, because it's already started, so to speak. These are 3/16, so that would fit in this type of holder. These are 1/4 inch, and those would go with this kind of holder. This and this are all 5/16, which is mostly what I use on my Hendy lathe. And that would be this size. Right. Well, here, just look at, well, this size that would be for these. And then that's the 3/8, and I don't think I have any 3/8 holders out here.
Yeah.
Oh, this one. Okay. So before you grind a tool bit, the first thing you must be aware of and pay careful attention to is what kind of tool holder are you going to put that bit in? Specifically, does that tool holder hold the bit horizontally or pitched up at an angle? That is super important for you to know before you start. So let's just look at the tool holders here. And what you'll see is all of these tool holders here, and I guess I moved some of them. Let's move these back. All of these tool holders hold the bit up at an angle. And that angle does vary. I wish I could tell you, oh, it's always 16 degrees. Now, some of the books, like Burkhart's books, say it's 16 degrees. But I got this out and I started measuring them. So you see what I've done here.
Yeah.
And I started measuring the angle of inclination. And I found that they vary from about 7 to 17. And there's a big variation. So, but almost all of these tool holders of the first generation had the bit inclined at roughly 15 degrees. And so here's 15 degrees, right? So what that means is that this is going to be inclined at that angle. And what we need to be aware of is if that's going to be up at that angle, then we have to have clearance for it, right? So the amount of clearance that you need in the front has to be calculated based on the angle that the tool holder is holding the bit. So that you have clearance here, you have clearance on the nose, and you have clearance here. So all the surfaces have to have clearance.
So the clearance you're talking about is
this
the
space.
gap between
This
the
space.
angle, but it's the space between
Yes.
vertical.
So that clearance angle, which should be 5 or 10 degrees, metal is actually bending less. And that allows this all to operate more smoothly with less pressure and less heat and less power consumption and less vibration and less chatter and less heating of the tool and less heating of the workpiece and so forth. So you want to have some slope back. And the sloping back is known as back rake.
Rake, and some people refer to it as top rake versus back
Some
rake.
people refer to
Yeah.
it as top rake, right? So
But
if that rake is sloping just straight back, okay, then that's back rake. If the top of the tool slopes to the left or the right, like this one, right? So then that's called side rake. So a tool like this could be held, it would have a back rake that would be imparted by the tool holder, and a side rake that's comes from the grinding of the tool. So it has back rake and side rake. There are many tool holders that do not hold the bit at an angle. They hold the bit perfectly straight out. And you would think, well, why would you want that? Well, what happened was in the 1950s, maybe somewhat earlier, carbide was starting to be used for cutting metal. Now here's a typical carbide bit. This is called a cemented carbide. This is before there were the little indexable carbide things that you screw on. Mm-hmm. These are brazed on. Mm-hmm. But this was the first and still a very popular and inexpensive type of carbide bit. You know, these are only a few dollars, really. So when you're using carbide, you don't want to pitch it up at an angle. You want to use it straight out. And so Armstrong came out with a new line of tool holders where the bit fits in here and it's held perfectly straight. It's not angled up. And these were designed for carbide. And some people call these carbide holders, but the earliest type of carbide was the tungsten type, and they call it tungsten carbide. So Armstrong started calling this the type T. So these are the type. So this is called a T2, right? So it has the letter T, and that means that it's designed for tungsten carbide, and that the bore, the square hole, is perfectly straight. So that's what these three tool holders are. They're the same in every regard to these older type, except that the holes are perfectly straight. Now there are other types of tool holders that also hold the bits perfectly horizontal.
So the reason for having no rake or a horizontal on carbide?
Yes, good question. Thanks, Dave. So carbide only has about half the tensile strength of high-speed steel. In other words, it's weak and brittle. And so the acuteness of the edge that you can achieve with carbide is much less. Let me show you, for example. Here's a tool holder. This is kind of an outlier because This tool holder holds the steel at 25 degrees. Now, I've successfully used this tool holder. This is one of my favorite tool holders to use on my metal planer. With this, notice how much clearance is ground into this, which it has to have because it's going into the tool holder at 25 degrees.
Yeah.
Now, the acuteness of this edge is very critical for efficient planing of soft steel like hot rolled plate, which I often machine on the planer. You could never grind a tool like this in carbide. Maybe you could for some kind of woodworking, but not for working metal because it would just be too fragile and the edge would just chip away. Because carbide just doesn't have the strength that high-speed steel has. So that sort of brings me to a really important point, is why should I use high-speed steel? Why don't I just get that carbide, then I never have to sharpen it, and I just put a new one on and I throw it away? Well, first of all, we're Yankees, and we don't like to throw things away. Now, I wasn't born a Yankee, but I've been here 40 years, and I've kind of become one. And I think part of being a Yankee is using things up. So what I'm going to talk about is among the advantages of high-speed steel and how it's a huge advantage for hobbyists or home shop machinists like us to be able to utilize geometry that's more varied and more effective on a small machine than what you can do with carbide. Because with carbide, you're very limited. You know, it generally has very little, if any, top rake. I mean, look at this bit. You know, this bit has side rake. Oh yeah? How much? Like 2 degrees, right? That's like hardly enough to do anything. But with high-speed steel, you can do so many things and get a really acute, sharp edges that will peel off that softer metal that we like to use, and that carbide could never do. And the other thing is, you know, maybe I'm just sounding like sour grapes, but I think that the generation of machinists that have always used throwaway carbide bits have never acquired the knowledge of what's possible. They've never acquired the knowledge of how rake angles can get results. Or, well, what happens if I grind it a little this way? Or what happens if I grind it a little that way? Let's put it on, let's try this. You know, they don't have that experience because they simply use this, you know, the boss says use that bit, you use that bit. When it's dull, you rotate it. So they haven't gone through the experience of trial and error, which is so fascinating and will show you that you can do things with high-speed steel that you can't begin to do with carbide.
So the inserts like allow you to do the exact same thing every time perfectly.
Yes.
But they don't allow you any opportunity to try slightly different angles or slightly different approaches.
Or to try very acute angles with very big rake angles that simply would not hold up if you tried to do it in carbide.
Particularly.
Here, I'll hold this up there. You see that sloping back.
Yeah.
So that pulls the top jaw down and in that direction and clamps the bit. Now, the head, when you loosen it, the head can be rotated this way, or this way, or this way, right?
Okay.
So they're very good. So in terms of the...
So you don't have to adjust your lantern or whatever you're using.
Right.
You could do it.
And, you know, you can even get access to reach around like the back of something, you know, this way, which you can't do with these. So these are really popular on shapers and planers because they have that. These are made by, this is made by Walton Company. Yeah, these, you want to get the close-up? These are made by Walton Company. Not Wilton, which makes those nice vices, but Walton. Okay. Now, most people today like these quick change tool holders, sometimes called the Aloris type tool holders. And I know why people love these, because the height is so easy to adjust. And you take this off and put it back on, it always comes to the same height. But here we have, this is the best of both worlds, right? Because here we have the Armstrong tool holder. All right, so this is a size 000.
It's the tiniest Armstrong holder you're ever going to find.
Right, it's a 000 fit in a size A quick change, and holds the 3/16 bits. put this in a lantern-type tool holder with a rocker, or you could put it in a different kind. But what I find is sometimes you can get very microscopic adjustment of the height by moving this in and out. Once you've gotten really close and you want to move it just a few thousandths, it's sometimes easier to pull that out a little bit rather than readjust there. But yeah. Whereas, these are more straightforward. This is more straightforward and foolproof. Every time you drop it on, it comes to precisely the correct height. And that's why people love them. Okay. We started out looking at this. And I talked about how this would be in a tool holder at a 15-degree angle. And at a 15-degree angle, it would still have clearance in the front and clearance and clearance.
How much clearance do you want in the front?
5 or 10.
Okay.
If this is the basic tool. Now, the nose of this, usually you want to make that about a little less than 90 degrees, 75 or 80 degrees, because that will give you the most versatile tool. Because if it's 75 or 80 degrees, it'll go into a square hole, a square corner. It'll go into a square corner. Yeah. If it's more than 80 degrees, you're not going to be able to get it into a square corner.
It's a lot trickier.
And that may or may not matter. You might want to go into the square corner as a second operation. But if you want to do your cutting and cleaning up of the square corner in a single step, you're going to need for this angle to be slightly less than 90. So let's just look at that and you see. Okay. So the angle is slightly less than 90, and that gives you the most useful tool. All right. So what's the difference between this and this? Well, if you're using a bit in a tool holder, either this type or this type or these types that hold the tool exactly straight out, you need to create your own back rake. And the back rake has to be ground into the tool. So this is just another version of this. I mean, you look at it from the front, the profile is the same. But when you look at it from the side, you see the difference. So this one has the back rake ground into it. So when you have a tool like this, and it's set at an angle, and it gets dull, you grind the nose only, and you never grind the top. You don't have to grind the top because that's built into the tool holder. That's the ideal system. That's what I'm calling a sustainable grinding system. Because whatever you do, you're only doing it in the front, and it just gets shorter and shorter and shorter and shorter. And then finally, like a Yankee, you've used it all up. And then you've gotten 1,000 sharpenings out of that one bit. Okay, in a very Yankee-like way. But when you have this, so this is what I'm calling incremental. It's not system. So as you grind this, if you're grinding the nose only, then this gets shorter and shorter and shorter, which for one thing makes this lower and lower. That may or may not be a problem. But eventually you get so close to the shoulder that the chips are going to jam up in here. So at some point, when you're already down here and you're so close to this shoulder, you say, okay, I can't do this anymore, and I'm going to lop that off and regrind again. So it's incremental in the same sense that this is incremental. Now, another variation of this would be this, which is also incremental in that if you're grinding the nose only, eventually you get further and further back until you get to that bottom of the curve where you don't have any back rake anymore.
You're also making a really interesting point that a lot of people miss is that there's shaping and there's sharpening. And I how many times I've run into people that are like, every time you go to the grinder, you got to like reshape the bit. It's like, no, you want to create the shape, and then you want to just touch it to sharpen it. I know it's basic. But.
Exactly. Well, I guess you sort of cued me to very quickly explain it. I've done a lot of talks on sharpening wood turning chisels.
Yeah.
And I usually would say this, that so many beginners say that they're confused by the sharpening. They look in lots of different books and they find the sharpening very confusing. Well, before I started writing articles on sharpening, I bought all the wood turning books I could find and see what other experts had written about sharpening. And when I read all the books that the beginners were complaining about, I understood why they were complaining. And that is essentially that almost all authors are combining two subjects into one chapter and mishmashing them together, and they should be in separate chapters. And those two chapters are, one, tool point geometry, and two, sharpening. So what that means is that if you understand tool point geometry, you understand why the tool is shaped the way it is, and what happens if you change that shape this way or that. Sharpening is simply the maintenance of the perfect edge.
GPS signal lost.
Oh well, I guess we don't know where we are now.
And assumes that you already have the correct geometry, and you want to maintain that correct geometry as you sharpen the tool hundreds or maybe even thousands of times. So these are two separate subjects and should be in separate chapters and not mishmash together in one chapter called sharpening. Always have to grind the nose radius. So let's just briefly talk about nose radius. Every one of these tools has a roundedness at the edge. You can't, and I hope that your camera will pick that up. Are special. You see how these are rounded? The roundedness of that edge is really important. If it's perfectly sharp, it's not only going to give you a really rough finish, but the that pointed corner is very fragile, and it's going to break down. So how much roundness do you want? On a small lathe, only a 64th of an inch is usually enough. But then you come to this. Okay, so what is this? I guess one thing to point out about this, this is actually a form tool, and it's really for doing inside radii, is that this comes in a lot of different varieties. For example, you see that. So here's one. So this one is the same width as the bit from which it was ground, and so the width of this could vary depending on the bit that you're grinding it from. But here you can see how the width of the brown nose is much smaller than the bit, and here's one that is way smaller. Right? And these are very useful for necking parts that are to be threaded. And anytime you want to make a neck with, you don't want sharp inside corners on mechanical parts because that's how cracks develop on sharp inside corners. So you generally want some kind of radius on the inside corner. How much really depends on so many engineering things I can't get into, but that's where these round nose tools are really important to make rounded inside corners. And just because, in this sample I've made it the full width, but normally you could make that round any size.
Want to pass those around, or
these?
The bits?
The little bit, yeah, because they're hard to see. All right, where was this one? And yeah, these are two. Okay. Now, what's nice about this, you can turn it different ways, right? So, why this crazy shape here? Isn't that going to be kind of weak and flimsy? Well,
meant to be.
The weakness of it is engineered into the system so that when there's pressure on the tool, it flexes from this point instead of from down here. And because it's flexing from up here, the pressure on the tool tends to move the tool away from the work instead of having it dig into the work. Right. So these types of tools are used in situations where you have chatter that you can't seem to quell, and these just work amazing. And this is kind of accomplishing the same thing, but it's not flexible, but it puts the cutting point below the suspension point so that it flexes this way instead of digging in. This is also a zero rake tool. This is one that I featured in my recent YouTube video. This is kind of a rare thing. It's made by Williams, and what's rare about it is it's a cam lock. It locks the bit in with a cam. Now, cam locks are very common on cutoff blades, but they're not common on square bit holders. So this is a kind of unusual thing. Doesn't look like it's ever been used. This is a 14 degree. Yeah. The other before I get to this other thing, the other thing that square bits are used for is in boring bars. So most of the commercially made boring bars have a hole at each end. So this hole is 90 degrees to the bar, and this hole is 45 degrees to the bar. So you would use this if you need to go into a blind bottom, a square off bottom. But for through boring, these are more convenient. Here's a smaller version of the same thing. You see how this would work to a square bottom. So this is another attempt to achieve sustainable sharpening in a completely different way. So on these type of holders, you only grind the top. So you see how this is a square bit, just like all the other square bits that we've used.
Oh, right.
And the only difference is that the edge of this bit has been rounded to create nose radius in the front. But these are so easy to sharpen because you take them out, you put that against the grinder, and there you go. You can give it left side rake or front rake, whatever way you want to grind the top. But as this gets ground, it simply moves up and up until, of course, it's too short.
Of course, your point is always 90.
Yes,
Yeah.
Your point is always 90.
Unless you...
It's actually a little less because it's tilted.
Yeah.
But it's difficult to go into a square corner with one of these. I have the taper attachment and the steady wrist. And I love this lathe. It's just it's the most rigid, and this lathe never vibrates or chatters. I've never been able to make it do that. So I'm very happy with it. The only thing I will say is that the gears are 100 years old, and you'll hear that in a little while. So I have a piece here between centers, and I don't think we're really not here to talk about how to run the lathe or how to mount the work, but
Okay.
I do most of my work between centers when I can, because then you can take it out and put it in, or you can take it out, turn it around, and you can take it out, put it in a different lathe or whatever, and you know it's always going to be perfectly centered every time you return it. This is a really important thing. So this is the Norton gearbox, the quick change gearbox, and Norton invented this gearbox and patented it. Here's the patent date, March 8th, 1892. And then he teamed up with Hendy, and Hendy said, this is great, I want to put this on all my lathes. And Norton said, great, let's design them to fit all the different lathes. And Norton became the superintendent of the Hendy plant, and they're in Torrington, Connecticut. Of course, they've been out of business for some time. This particular lathe was made in 1918. So in order to take a heavy cut, we want to put this in back gear, and that means is I'm going to engage the reducing gears in the headstock. So the first thing I want to do is pull the pin that connects the pulley to the spindle. So now this is not connected anymore. But I want the powertrain to go through this gear train here. So I've engaged the back gears now. So now I have a reduction of about 7 to 1. finishing cuts that are very shallow cuts, that when you peel the cut away from the finished side, it cuts more cleanly than if you're trying to peel the cut from the cutting side. So instead of pushing the metal toward the finished side and having it break away, you're shearing it away from the finished side, and it gives a smoother finish. So it seems contrary to logic to have the side rake be backwards, but it's not really side rake. It's simply a shear angle. So now you see it's held on by these things. These are called toe dogs. I have a video on the Guild YouTube channel that describes exactly how to set these up and why they're set up the way they are. So I would refer you to that video. The name of the video is Setting the Toe Dogs. And it's my second most popular video. Okay, so now with the light, get over here, Dave. So now with the light there, I can really see as I lower this down.
Oh yeah.
Right, I got to do something here. So you got to make sure that you have enough tension here so that the thing doesn't fall by its own gravity. In other words, you want to be, there's backlash.
Yeah.
You want to be pushing it down. You don't want it to be falling. Okay.
Just looking at the light under the, yeah.
You know, I did this before, and I know I've got the dial up here,
Yeah.
and I'm watching that. So,
Close.
okay. Right about there, right? So, like most shapers and planers of that period, the reversing of the table is accomplished by the reverse belts. So, one belt's moving down and the belt's moving up. And that's accomplished, of course, by crossing the belt. Now, interestingly enough, it's the crossed belt that is the forward feed for the cutting stroke. And that's because a cross belt actually grips better than a straight belt because it wraps around the pulley more than 180 degrees. So this is the return belt. And if you look up there, you'll see that the drive pulley for the return belt is bigger than the drive pulley for the forward belt because you want the return stroke to occur faster just to save time. Going back to this advertisement for Armstrong Tools from 1909, I'd like to draw your attention to this one on the lower left. This is an interesting kind of tool holder, and it's labeled here as a planer tool. Certainly in the large sizes it would be used on a planer, but I have one here that I use on my shaper. Taking a close look at this tool, it's clear that the head can swivel in different directions, just like the Walton. In other words, we can take the bit out and turn this to a different way. And now we have the tool on the side. So this makes it very useful. When we look at this tool, we think that it could be used on a lathe or a planer or a shaper. But it's not absolutely clear whether the bit is supposed to go in this way or is the bit supposed to go in this way to be used this way? Well, certainly if you're using this in a lathe, you would probably use it this way, because you need the bit to be more or less even with the top of the tool. Because in this position, you would never be able to get the tool high enough to come to the center line of the lathe. What I've learned from using this tool on my shaper is that it works much better in this position. The cutting edge is on top, and the position of the tool is below the center line of the shank. And that gives a lot less chatter and vibration to the tool, because the pressure is below the pivot point of the tool. So let's see how this fits into the shaper.